Let us now see how we can do hypothesis testing on the regression parameters. As we discussed earlier, out of the two regression coefficients, beta naught and beta 1 is more important to us because beta 1 will tell us whether there is any association between x and y, and if yes, then to what degree. Now, therefore, one is typically interested in making inferences on beta 1. And if we refer back to the sales versus advertisement problem, then we may be interested in finding out whether there is any association between advertisement and sales. By making Shah Rukh Khan endorse the brand Pepsi by spending more on advertisement, am I really going to increase the sales of Pepsi or not? Right? So here my null hypothesis would be the status quo, which is beta 1 equal to 0, because a priori we do not have any reason to believe that there is an association between advertisement and sales. And we are testing it against the alternate hypothesis that beta 1 is not equal to 0. So what would be a good choice of test statistic in this case? I can choose a test statistic, which is the difference between beta 1 hat and 0, right? So this test statistic, if I choose, so let us use the notation T to denote the test statistic. It can be the difference between beta 1 hat and 0. It will tell us how far our estimate is from 0, which is the value against which we are testing. However, how far is far enough would depend on the standard error. So we will divide it by the standard error of beta 1 hat. Recall, we are familiar with these concepts now from our discussions in module 2 on testimation. So we define a test statistic T like so. And we also know that here for simple linear regression, the critical value T critical is given by T with n minus 2 degrees of freedom and 1 minus alpha by 2, where alpha is the chosen level of significance. So we can test the null hypothesis and reject it based on the evidence in the data or not. So we can reject H naught or not reject H naught based on either a fixed confidence or based on the p-value. So if I write it for the fixed confidence level, then again from the earlier concepts on testimation, on hypothesis testing that we discussed in module 2, these are just extensions of those concepts. So we can reject H naught at 100 into 1 minus alpha % confidence if the modulus of T observed is greater than this critical value, T critical, right? I can also write the expression of p-value, which would be the p-value, because this is a two-tailed test. The alternate hypothesis is that of not equal to. So this would be 2 into the probability that any t by virtue of chance alone is greater than the observed value under the null hypothesis. So again, if the p-value is low, means that probability that we would have observed a t test statistic as extreme as the one we have indeed observed under the null hypothesis. If the probability of this whole thing is low, we know that T observed, what we already have observed, is what we have observed. That's the reality. We cannot change that. So if the probability is low, it means that this under H naught part. The, the assumption that H naught is correct must be wrong. So therefore, if the p-value is low, we reject the null hypothesis. So this is how we do hypothesis testing on beta 1. Following similar principles, one can also do hypothesis testing on beta naught as well. So in the previous slide, I explained to you how to carry out a two-tailed test on the regression coefficient, which basically will be the third case here in this table, where we are testing the null hypothesis that beta equal to a certain given value beta star, which in the previous example was 0, because we were testing whether sales is affected by advertisement, and the alternate hypothesis was that beta 1 is not equals to 0, and this is what we had noted in the previous slide. If we are to do a one-tailed test, that is, our alternate hypothesis is to see whether beta is less than a given value or greater than a given value, and of course the null hypothesis would be the complement of the alternate. Then you see that the expressions of the critical value changes a little bit. So instead of 1 minus alpha by 2, these are alpha here, and the probability, the p-value, is also given by these probabilities. So this is just to give you an idea of the fact that not only can we do a two-tailed test, but we can also do one-tailed test. And this is of course this is generic. You can do this on any hypothesis testing. So any hypothesis testing, if you're doing anywhere in statistics, you can either do a one-tailed test or you can do a two-tailed test. The critical value will depend on whether you are doing a one-tailed test or a two-tailed test. So let us now look at the t-table and how we can read the t-table in order to get the critical values. So in this axis across the rows, we have the degrees of freedoms, right? And along the columns, we have the cumulative probabilities. So suppose we choose an alpha which is equal to 0.05. So 1 minus alpha by 2 would be 0.975. And we can either look at where in this subscript here where 0.975 is, or we can simply take, so this table in particular has these two rows also, which directly gives the alpha values. So for the two-tailed test, we can either refer to the alpha, which is 0.05, or we can refer to 1 minus alpha by 2, which is this subscript here, right? And let's say we had 30 data points to which we are fitting simple linear regression. So then my degree of freedom would be 30 minus 2. So we have to look at the row corresponding to 28. And therefore my t in minus 2, 1 minus alpha by 2 would be 2.048. So this is how we interpret the t-table. So all this while we have been talking about this student's t-distribution. You know, who is student? I mean, is it someone's name? We credit the information matrix to Ronald Fisher. We credit particular concepts that we use. If it is proposed by a scientist, we credit it to that scientist's name. So why is it that students' t-distribution is so called? The person who actually is behind this is William Seeley Cossett, and he was an Irish brewer. He used to work for a company which is called Guinness, and Ireland, as some of you may know, is famous for its breweries. So William was working in a brewery, and he was very interested in statistics, and he used to work under the mentorship of Professor Carl Pearson, which I'm sure many of you would have heard Pearson's name. The correlation coefficient that we use is called Pearson's correlation coefficient, and so on. So in that context, you may have heard of Carl Pearson's name. So William Seeley Gossett worked under the mentorship of Carl Pearson, and while he was working for the brewery, he started publishing some of his statistical analysis and theories. And the company was worried that their confidential data might come out in the public domain. So therefore they gave him a warning that they he should not be publishing those data sets, and he should not be publishing any of his analysis on them. So William Seeley Gossett took the pen name of Student and started publishing by the name of Student. And of course, William Seeley Gossett was also a close friend of not only Carl Pearson but also Sir Ronald Fisher. So they were all contemporaries, and their works are also pretty much interlinked with each other. These are all phenomenal statisticians who developed this field, and some of these concepts are used to this date, so and they're so generic that they can be applied in many different contexts. So that's a little bit about who Student really was.